This video compares a recursive loop with an iterative loop. In addition, it illustrates the concept of stack frames, essential for understanding recursion. Let us start by considering this computer program here, and we're going to look at this function first. And you can see the name of the function is inc_print, and what the function is going to do is to print out the value of I as it's incremented. Now the mechanics of this function are shown here, and you can see that it's a loop. More to the point, you can see it's an infinite loop because I'm setting this here to true, which means the program will execute this over and over again until the user of the program decides to stop the program by pressing Ctrl+C. Now when the program executes, the first line to execute is this one here, where num is assigned 1. And on this line we make a call to this function, and you can see here that I'm passing in num, which is the variable that was declared on this line. And of course this variable here has the value of 1, so what we pass to here is 1. Then we go into the function, enter this while loop, and what this will do is print on the visual display unit the value of 1, because that's the value was passed in here. Then we come to this line, and what this will do, it will increment the value of I, so it'll become 2. And of course we then come back to here, and what this will then do is print whatever's in I, and of course we now know that I is now holding 2, so it'll print 2 to the screen. Then we come to here, we increment again, then we come back to here and we print it, and of course it'll now be 3 because it's 1 bigger. Then we come here, and of course I now is 3 here, but then we add 1 to it, which is 4, so I now will be given 4, and of course when we come back to here we will print that, and we will see 4 is printed. And the runtime for that you can see here, and you can see I've paused the runtime, so we can see that the first 4 are indeed 1, 2, 3 and 4. I will let the runtime run on, and you can see that the output is increasing by 1 every time we go round this loop. I've just paused the program so we can have a look at where we are up to, and we can see that here we're in the 600s. Now a question I would like to ask, if you look at the program, how much longer can we go round the loop? In other words, how many more times can I perform this incrementation and assign the results to I, so we continue going round printing on this line the bigger and bigger value of I? Well, let's let the program run on, and I'll come back and have a look at the runtime and see where we're up to. Well, if you look to the output, you can see it's now printing numbers in the 5,000s, so it's having no difficulty getting I up to numbers that are in the 5,000s. Here you can see I've let it run on again, and it's having no problem going up as far as 23,000, and it will eventually get to 24,000 and beyond. So we can see here quite clearly that this program is having no difficulty printing out a list of numbers that get 1 bigger, and that is possible because we can take the value of I in our Python program to a very large number, and I'll let you give some thought to how big that number may be. Perhaps you might like to enter this program and see how far you can get the value printed out. How high will it go when you use I in this way within this loop? I'm now going to move on to this computer program, and what it will do, it will also print out the incrementing of I to the screen, so it'll print 1, 2, 3, 4, etc. But it does it in a different way. So let's have a look at the program and see what it will look like when it executes. If we consider this line, you can see I'm assigning to num 1. Now that's no different to the previous program that contained a function with the while loop. And here you can see that I'm invoking this function here. But have a look inside the function, and you can see that there is no while loop. So let's trace the execution of the program, and you can see on this line NUM is given 1. Here we call the function, and this value of 1, which will be in this variable, is passed to this. And on this line we then print out that value of I, so it will print 1 to the screen. If we come to this line, have a look at what it is, and you can see it's a call to this function. So within the function we have a call to the same function. Now what we need to realize is happening here is the following. This is set to 1. This 1 is then appearing here as the argument to the function. That argument is passed here to the formal parameter, and on this line we print out the value of the formal parameter, which will be 1. On this line we're calling this function again, and if you look in the brackets here you can see we're passing in I plus 1. Now clearly I is currently 1, so if I now add to that 1 the value of 1, this will be 2. So when this calls this function, the value of 2, which was worked out here, will be passed to this I here, and this will then print that value of I, so 2 will now be output to the visual display unit, and then again we call on this line this function. But if we refer to this argument here, it is now I plus 1, and we've just seen that I was equal to 2, so this will become 3. So when this calls this function, the 3 that was worked out here will now be passed to this I, and this I being the value of 3, when we come to this line, that is what will be printed out, 3. And then of course we call this function again, but on this occasion what we're passing in here is I plus 1, which is 3 plus 1, which is clearly 4. So the 4 will appear here, and this then will print out that value of 4. Let's consider the runtime for this computer program, and here you can see the runtime, and you can clearly see that it is outputting the value of I, and that value is getting 1 bigger each time it is output. So it would appear that this program is working in exactly the same way as the previous program, but keep your eye on it and you will notice that it crashes. Now what I'm going to do is scroll up here and have a look how far it actually got. We can see that it outputted bigger and bigger values of I, with I increasing by 1 each time, and it got as far as this value here, 1012, and then the program crashed. Now the question we need to ask is, why does this program only allow us to go as far as 1012, whereas when we had the while loop we were able to go round the loop many more times? To assist in understanding why this program crashes, let's consider the feedback Python gives us at the moment of the crash. And the line I am interested in is this one here. And if I read what it says, recursion error, maximum recursion depth exceeded. In order to understand what this means, we need to consider stack frames, and that's exactly what I'm going to do for the remainder of this video. You can see I've placed both of the programs we've considered side by side. If we look to this definition of the function, we can see here we have a while loop, which means we're going to go round the loop, executing these statements numerous times. And every time we go through the loop, we increment I on this line. So it is quite clear with this function we have an iteration, i.e. this while loop here, and we're going round and round it, printing off I and then incrementing I. And here you can see we initially set this variable to 1. This then calls this function, passing in here 1 to this position, so when we first enter the loop here 1 is printed, and then we increment the I, and then we come back to here and print the new value of I. So what this program is demonstrating, it's demonstrating a design that is iterative in nature. In other words, it has a programming structure that is a loop, an iterative loop. Now if we consider this computer program, we have the definition of the function here, and if you have a look at the statements within the function, you can see we have a print I, and then we have a call, and this call is to the same function definition. But what we need to bear in mind, if we look at the function, there is no while loop here, there's no iterative loop, So what we can say is that this does not implement its design using iteration. This has a recursive loop. Now what that means is this line will call this initially, and this value here will have 1 that's passed to here. This will then print the 1, and here we can see we have a call to this function. And of course we pass in the 1 plus the 1, which is 2, and this function will then print the 2. And then here we have another call to this function. So there's your loop. You see, this function has a call in it to call this function, which then has a call in it to call this function, which then has a call in it to call this function. So although we can't see a loop as we can see here in the code, here we have to appreciate that a looping process is taking place, but it's not implemented by a loop as this function is. It's not an iterative loop as you can see here. We have also shown in this video that this program will print bigger and bigger values of I to very large values. I showed them going up to 24,000 plus, and you were advised to maybe run the program and see how big the number could be. This one here, however, if you remember, only got as far as 1012, at which point the program crashed. Now that may at first sight seem a little bit odd, because if you consider both functions, they're both dealing with I. But here we were able to get I to go bigger and bigger and bigger, whereas here there's a suggestion that we could only get I up to 1012. However, it's not the value of I that's causing the problems with this program to cause it to crash. It's something to do with how many times it is possible for a function to have a call within it to call itself. And there is a limited number of times that can happen. Right, I'm going to remove the recursive function call program from view, and I'm going to concentrate on the program you can see in front of you. And what we know is we really have two parts of this program. We have this part here, which is the main part, and this is the function definition that's called from the main part with this line here. Now, when this executes, what we have to bear in mind is that programs are stored in computer memory. And when we look at this area, it's given its own area of the computer's memory, as I'm illustrating with this schematic diagram here. The blue area represents the memory, and within that area we have the two program statements and the variable declared. So there's space for this variable, which you can see has been assigned 1. And this line is going to call this function. Now, when this function is called, memory space has to be given over for this function. And I'm going to show that appearing here. And within this square blue box, you can see I have the definition of the function. And this function requires this area of memory. If we consider this area of the computer's memory, you can see it stores everything that is needed by the function definition. And what I mean by that, space will be set aside for this value of I here. So within the blue area shown here, there will be space set aside to store the values that belong to the variable I. And on this line, we're printing out whatever the value of that I is. But here, you can see we're incrementing that variable. But what I would like to stress, within this blue space, there is only one variable I. There are no more. So if I come over to here now, and we think of this bit of the code in terms of the variables it has, not the program statements, the variables, it just has one variable. It has this NUM, an abbreviation for number. Whereas if I come over here, in terms of variables, it has the variable I and no others. It just happens that the variable I here is a formal parameter. It's passed whatever was stored in here to here. And of course this goes around the loop now, printing out ever increasing values of I. Let's now consider the program that has the recursive calls, and we can see that appearing here. Now, when this program executes, we know that this area is going to have its own space, which I'm showing here, and that's no different to the program we've just looked at. But of course, what we can see on this line is we're going to be calling this function. Now, this function is given its own space, as you can see here, and we have I being passed the value from this variable, and I is indeed the formal parameter waiting for the value to be passed from here. And then of course we print I, but this now calls the same function, this function here. Now when we call it again, we have to realize that what will happen is this new runtime of the function will have its own space, as you can see here. Now, of course, what we can say about this space, it has its own copy of I, which will have been passed 2 from here, because this was 1, and we're adding 1 to it to give 2, so 2 is passed to here, so this will now print out the 2, and of course this will now call this function again, and this function will require its own space, as you can see here. And of course this I will have received 3, because what this would have worked out to be here would have been 2 plus 1, which is 3, which is passed to here. This then prints out the 3, and of course we now have another call to the function here, and this will be 3 plus 1, which is 4, so 4 will be passed to the function, and you can see that that function will receive its own space, as you can see here. So this I on this occasion will receive 4 is printed out, and then you can see here we're calling the function again. Now I've run out of room on the slide to show more space being created, but there would be. And the thing is, every time there is a call, as this is, this call will result in this space being created. This call will result in this space being created. This call will result in this space being created, and so on. Now, if you think about what happened when this program executed, we got as far as 1012. Now, what that is suggesting to me is there's a limit to how much of this space can be created. It was fine in terms of getting as far as 1012, but when we then tried to create some more space, the program crashed, because there is a limit to how much space you can set aside for every new invocation of this function. Now, as a human being and a computer programmer, we might look at this definition here and say, oh, well, it's got the variable I, and what we're doing, we're printing it out, and then I'm adding 1 to I. So it kind of suggests there's only one value of I. In the same way as when we look at this bit of the code, we can see here there's just one variable, num. Well, the truth of the matter is, when this calls this for the first time, this is created, and this value of I belongs to this space. Of course, when this calls the function, it creates this space, and this will have its own copy of I. So whereas a human being, we might look at all these I's and think, well, they're the same variable. Well, they kind of are, in the sense that they are the variable that was defined in this definition, but you can see they've all taken up their own space. So they are independent of each other. They just happen to have the name I, as we can see here. Of course, this may confuse us as a human being looking at the value of I here and saying, well, isn't this the same value of I that was defined over here? And the answer is, well, as far as the language is concerned, no, because it has an underlying mechanism that creates space for every time a function calls itself. So the programming language, the underlying mechanisms, have no issue with creating this space for each new recursive call to the same function. However, the language can only do it so many times. And we have seen for the program that I produced, we got as far as 1012 and it couldn't make another call. In other words, it didn't get to 1013. It crashed. So let's emphasize this point. This part of the program here will have its own space, as I've shown here, so it'll have space for its own variable num, and this is now a call to this function, so space will be created for this function, and I'm going to show that here. and I'm saying that this red area is the space for the first call of the function, and it's got its own copy of I. And of course, I put in brackets here that it will have the value of 1, because on this line, num is assigned 1, and here we're passing 1 to here. So this invocation of this function results in this area of space where I has the value of 1. Now, of course, the function will call itself. And of course, this new call will create its own area of memory, or Python will create that area of memory, and we can show that here. And it will have its own copy of I, which will store the value of 2. Because when we called this, remember I was already 1, and we're adding 1 to it, which gives 2, so that will be 2. And of course, this new call will cause this to execute again, and this is 2 plus 1, which is 3. So that function will have its own space created, as I'm showing here. And it will have its own copy of I, which I'm showing here as being 3. And of course this will carry on, which is what I'm showing with those squiggles. And eventually I, getting bigger and bigger and bigger, and we're creating space for every new call of the function, every new recursive call. So we will eventually get to a call which will have I at 1010. And then, of course, this will recursively call the same function again, and it will now have its own copy of I, which is 1011. And within that function, there's a call to the same function, so it's a recursive call again, and of course, this new execution of the function will have its own copy of I, which is 1012. Now, of course, this new function will attempt to call itself, i.e. this function here, and will be passing in I plus 1, which will be 1013. But if you remember, when we run the program, it crashed. And the line I'm interested in looking at from the feedback given to the programmer by the crash is shown here. Recursion error, maximum recursion depth exceeded. Now what this is telling us is you can only have so many of these areas of memory set aside for each call to the function, each recursive call. And this number here for the program that I showed you appears to be as far as we can go in terms of setting computer memory aside. So if I remove that for a moment and we look here, each one of these is not much memory, but you can see there's 1012 of them. And of course, if we look at this function, we've only got one variable. Well, imagine you've got a function with many, many variables. Each area would then have more space needed. And of course, we'd have to repeat that space for every time we have a recursive call. So these areas of memory here individually would all be the same size, because they'd all have the same variables they need to store. And they could be quite big in terms of the memory space needed for the variables. And of course, a computer has a limited amount of memory. So you can't go on forever setting aside memory, because as you've seen, the program will crash. Now there's a lot more to this. You can actually write your code in such a way that you can alter the depth of how many times you can call a function, but I'll leave that for another time. Here we've seen with the code we've looked at, there's only so many times we can actually create space for each new recursive call of this function. If we return to this computer program, which will output the incremented value of I to a very large value, because the limit on this is really how big we can have I. And in Python, the value of I can be very big. So when we run this, what we need to bear in mind is space is set aside for this bit of the code, and space is set aside, as you can see here, for this bit of the code. So there are only two areas of memory set aside, and that's not going to chew up the computer's memory, is it? You see, this will have the variable num, and this one will have the variable I that's just getting bigger and bigger every time we go round this loop. Whereas if we consider this computer program, what will happen? This area of the program will have its own space, and this will of course call this function. So space will be set aside, and each call will set aside more space. Now I've just showed it going so far. But we can clearly see that this computer program requires more memory space to be set aside, so the language gives you a limit to how much memory space you can set aside, because ultimately there will be a limit. For this computer program, you can see that 2 areas of memory have been set aside. This area is for this bit of the program, and this area is for this bit here. Now, it's not usual to show memory set aside side by side, as you can see here. It's usual for them to be stacked on top of each other, as you can see here, and for that reason they're referred to as stack frames. So this is the stack frame for this bit of the program, and this is the stack frame for this bit of the program here. And of course this frame will have a variable NUM with the value of 1, and this frame will have a variable set aside called I, and that value of I will increase every time we go round this loop. So here you can see we've got stack frames, and that's the normal way in which we would look at the memory for an executing program. If we come over to this computer program, you can see I've got this memory area here for this bit of the code, and this memory area is for all of the calls to this function, where we have a recursive call, which, just to remind you again, is this calling itself. And we don't usually show these in the way in which they are laid out. We show them usually like this, also in a stack, and these are examples of stack frames. So this one here is for this bit of the program, so this will have a variable set aside called NUM to store, in the case of the program here, 1. This will have memory set aside to hold the I, and this I in the case of this program would be 1. This stack frame, well, that will also have memory set aside for the variable I, and it will have the value of 2, and so on. So it is usual for us to show stack frames, and we usually concentrate on the variables that a stack frame gives us. So this one here, for example, would have a variable NUM. This one would have a variable for I. This one would have a variable for I. This one would have a variable for I, and this one would have a variable for I. But of course, these values of I's from the perspective of the runtime can take up different values, because they are different variables stored in different areas of the computer's memory. As a computer programmer and a human, we may be thinking, well, isn't this the same I? Well, the answer is no, it's not, because each call to this function sets aside room for a new copy of I. So it's important that we realize when we have a computer program that exhibits recursive calls, we will have a situation where stack frames are created, as shown by this schematic animation. Each one of these is an area memory set aside for the call to the function from within a function, and these are referred to as stack frames. Now, what I haven't shown in this video, but the previous video in the playlist did refer to the fact that it is usual for a recursive function to have a base case. In fact, if you don't have a base case, you're never going to leave the function. You have to have something that stops you going round and round calling the same function over and over again. In other words, there has to be something to terminate the recursive calls. Now, when that happens, the stack frames are removed one by one, because if this is dealing with the function, that's the base case, what it would do typically is return a value to here. So this stack frame is removed from the stack, as you can see here. Then the next one is removed, then the next one. And this removal is taking place. But before the removal takes place, you usually have the situation where something is returned to the function that called it, and we'll be looking at that type of example in later videos in this playlist. Check out the supporting website for these videos, and also consider subscribing to the YouTube channel. In addition, why not follow me on Twitter, as I issue a tweet every time I upload a new video.